Hello everyone, welcome to our presentation. Today we're going to explore Python control structures. This is the first slide, so I just want to quickly introduce the topic. We'll be covering the key control structures in Python that help us make our programs more dynamic and efficient. Over the next few slides, we'll dive into different types of control statements, how they work, and see some practical examples. I'm excited to get started, so let's jump right in. Let's take a look at the contents of today's presentation. We start with the introduction, setting the stage for our discussion. Then, we move into control structures, which are essential for managing the flow of our programs. You'll see how the if-else structure plays a key role in decision-making, followed by broader control structures that help us organize complex logic. We'll also explore examples of using loops, which are fundamental for repeating actions efficiently. Along the way, there will be a class activity to reinforce what we've learned. We'll dive into specific types of loops, like the while repetition structure, and for loops, with practical examples. Logical operators and their use in making decisions will be covered extensively, including how they combine conditions, with real-world examples. We'll also look at the pass statement, a simple but useful way to do nothing when needed, which might seem trivial but can be quite handy. Throughout the presentation, you'll see various code examples that illustrate these concepts in action, helping you understand how to implement them in Python. We'll also discuss the advantages of Python as a language, especially its readability and simplicity. Finally, we'll wrap up with a summary of key points, highlighting the importance of understanding control flow, logical operators, and syntax to write effective programs. And of course, we'll conclude with some thoughts on how these control structures empower you to create more dynamic and flexible code. Let's talk about the control flow of statements in a programming language. Essentially, control flow describes the order in which individual instructions or statements are executed within a program. It's like a roadmap that guides the program through different possible paths depending on conditions or loops. I'll show the control flow visually, but what's most important to understand is that control flow determines how the program moves from one part to another, whether it's sequential, branching based on conditions, or looping back repeatedly. This concept is fundamental because it directly impacts how a program behaves and how we structure our code to solve problems efficiently. Understanding control flow helps us write clearer, more logical programs that do what we intend. It's a key piece of the overall puzzle in mastering programming. Let's talk about control structures in Python. First, there's the sequential structure, which is built into the language and executes code line by line in order. This is the most straightforward flow of execution. Next, we have decision or selection structures, which allow our programs to make choices. The simplest is the if statement, where we execute some code only if a certain condition is true. Building on that, there's the if-else statement, which lets us specify an alternative block of code if the condition is false. Then, there's the if/elif/else chain, which is useful when we have multiple conditions to check. It helps us handle various cases in a clean, organized way. Finally, we look at repetition or iterative structures, which are essential for repeating actions. The while loop keeps executing as long as its condition remains true, perfect for scenarios where the number of repetitions isn't known up front. On the other hand, the for loop is ideal when iterating over a sequence, like items in a list, making it very useful for controlled repetitions. Together, these control structures form the backbone of programming logic, allowing us to build dynamic and responsive programs that can handle different situations and data effectively. Let's talk about the sequential structure today. This is the foundation of how most programs execute. They follow a normal flow or sequential execution of statements. Think of it as reading a set of instructions line by line, in order. For example, if you want to perform a simple addition, you might have variables a and b assigned values, like a equals 5 and b equals 6. Then, to get the sum, you simply print a plus b. In code, that could look like print a plus b. It's straightforward and easy to follow. Another key point is updating values, such as adding a grade to a total. You might see a statement like total equals total plus grade, which means you add the current grade to the running total. And don't forget about counters. You often need to keep track of how many times something happens. So to add 1 to a counter, you'd write counter equals counter plus 1. This step-by-step, line-by-line execution is what makes programming logical and predictable. It's the core concept that helps us understand how instructions flow in a program, connecting everything back to the overall theme of structured and clear code. Let's take a closer look at the sequence control structure. As shown in Fig. 3.1, we have a flowchart that illustrates how a sequence operates, along with some pseudocode to help clarify the concept. The key idea here is that in a sequence, the instructions are executed one after the other, in a specific, linear order. This is the most straightforward control structure, and it's fundamental to understanding how programs run. The flowchart visually represents this flow, starting at the top, moving down step by step until reaching the end. The pseudocode underneath shows how this looks in actual programming language, emphasizing that each statement follows the previous one without deviation, unless we introduce other structures later on. Understanding sequence is crucial because it forms the backbone of any program. Everything we do, whether it's calculating a value, displaying information, or updating a variable, follows this linear flow. This structure helps us build more complex logic by combining sequences with other control structures. So, as we continue, keep in mind that the sequence is the foundation. Mastering it will make understanding more advanced concepts much easier as we progress through this presentation. Let's take a closer look at decision control flow. Essentially, this is about making choices in our programs based on certain conditions. Think of it as a decision point where the program evaluates a condition, and depending on whether that condition is true or false, the flow will follow a specific path. In our example, the condition is whether the grade is greater than or equal to 60. If this condition is true, meaning the student has passed, the program will print passed. On the other hand, if the condition is false, the program will follow a different path, possibly to handle a failing grade or other logic, but that part isn't shown here. The key takeaway is that decision control flow allows programs to make dynamic choices, ensuring that the right actions are taken based on different scenarios. This concept is fundamental because it helps us create more flexible and responsive programs. It's a core building block in understanding how to direct the flow of logic based on specific conditions, which ties directly into the overall theme of programming logic and decision-making. Let's take a closer look at the if selection structure, specifically through the flowchart shown in Fig. 3.3. This diagram illustrates how a simple decision-making process works in programming. The key idea here is that the if statement allows the program to make a choice based on whether a condition is true or false. If the condition is true, then a particular set of actions is executed. If it's false, those actions are skipped, and the program continues on its path. This structure is fundamental because it introduces decision-making, enabling programs to react dynamically to different data and scenarios. Connecting this to our overall theme, understanding selection structures helps us write more efficient and flexible code, which is essential in creating responsive software. So remember, the if structure is like a fork in the road, guiding the flow of your program based on specific conditions. Now let's take a closer look at the if-else structure. In this example, we're checking whether the grade is greater than or equal to 60. If the condition is false, meaning the grade is below 60, the program will print failed. On the other hand, if the condition is true, meaning the grade is 60 or higher, it will print passed. This setup illustrates a double selection structure, where the program chooses between two options based on a single condition. The flowchart in Fig. 3.4 visually represents this decision-making process, helping us understand how the program flows depending on the student's grade. This kind of control structure is fundamental because it allows programs to respond differently based on varying inputs, which is essential for creating dynamic and interactive applications. Now let's take a look at our class activity. The program we're discussing checks whether a number is positive or negative, and then displays an appropriate message based on that. For example, if we set num to 3, the program will recognize it as a positive number and print positive or 0. But you can also try different variations, like setting num to -5 or even 0, to see how the program responds. The key point here is the use of a simple if-else statement to determine the sign of the number. If the number is greater than or equal to 0, it prints positive or 0. Otherwise, it prints negative number. This logic is fundamental in programming because it helps us control the flow of our code based on different conditions. Another important aspect is that the program can be modified to get input from the user, making it more interactive. It can then check whether that input is positive, negative, or 0, and respond accordingly. This approach of combining input handling with condition checking is a great way to make your programs more dynamic and user-friendly. This activity ties into our overall theme of understanding decision-making in programming, how we can use simple conditions to make our code intelligent and responsive. Let's continue exploring the if/elif/else selection structure. As you can see, this structure allows a program to make decisions based on multiple conditions. The key point here is that the program checks each condition in order. If a condition is true, it executes the corresponding action and skips the rest. If it's false, it moves on to the next condition. For example, it starts with an if statement, which checks condition A. If condition A is true, it performs the associated actions. If not, it evaluates the first elif statement, which checks condition. If condition B is true, it executes its actions. This process continues through multiple elifs, each checking different conditions, like condition Z in the last elif. And if none of these conditions are true, the program finally defaults to the else statement, executing whatever default actions are specified. This structure is powerful because it allows for complex decision-making with clear, organized flow control. It's a fundamental tool for handling multiple possible scenarios efficiently and logically within your code. Let's talk about syntax. Syntax is essentially the set of rules that define how we structure our code or language. It's the grammar of programming languages, ensuring that everything is written in a way that the computer can understand. When we think about syntax, we're focusing on the correct arrangement of symbols, keywords, and expressions. Getting the syntax right is crucial because even a small mistake can cause errors or unexpected behavior. It's what allows us to communicate clearly with machines. Throughout this presentation, we've seen how proper syntax underpins all the programming tasks we've discussed. It's the foundation that enables us to build more complex and reliable systems. So, mastering syntax is a key step in becoming proficient in any programming language. All right, now let's take a look at some example Python code. Here, we're going to see how these concepts come together in a practical way. The code will illustrate the key points we've discussed so far, such as data handling, processing, and perhaps some basic analysis. As we go through it, I want you to focus on how the structure of the code reflects the logic we've been emphasizing. Notice how functions are organized, how variables are named for clarity, and how comments help explain each part. This example will help solidify your understanding by showing how these ideas are applied in real-world programming. So, let's dive into the code and see these principles in action. All right, let's walk through this example with Python code. First, we prompt the user to enter the price of 1 tomato, and we convert that input into a float. This allows us to handle decimal values easily. Then, we use an if/else structure to decide what message to display based on the price. If the price is less than 1, we say, "That's cheap, buy a lot." If it's between 1 and 3, we suggest, "Okay, buy a few." Otherwise, if the price is 3 or more, we tell the user, "Too much, buy some carrots instead." Finally, we print out the message stored in S. This example highlights how conditional statements can be used to make decisions in your programs. It also shows how to get user input, convert data types, and output different responses based on that input. Connecting this to the overall theme, understanding conditionals is essential for writing responsive, interactive programs that can adapt to different situations. Let's move on to our next topic, control structures. These are fundamental building blocks in programming that determine the flow of our code. They help us make decisions, repeat actions, and manage complex processes efficiently. The most common control structures include conditional statements like if, else, and switch, which allow us to execute certain code only when specific conditions are met. Then we have loops such as for, while, and do while, which enable us to repeat actions multiple times, saving us from writing redundant code. Understanding how to properly use control structures is key to writing clear, effective, and maintainable programs. They connect directly to the overall theme of building logical, dynamic solutions in programming. Mastering these tools gives us the power to control the execution flow and create more sophisticated applications. Let's take a closer look at what this slide is telling us about control structures. So here we have a condition, true, which checks if the product is less than or equal to 1,000. If this condition is true, then the program sets the product to twice its current value. And if the condition is false, then the program would follow a different path, which isn't fully shown here but is implied. The key point to understand is how control structures like this allow us to make decisions in our code based on certain conditions. They help us direct the flow of execution dynamically. This concept ties into the overall theme of programming logic, using conditions to make our programs smarter and more flexible. So, mastering control structures is essential because it enables us to handle different scenarios efficiently and effectively. Now let's take a look at the while repetition structure, which is illustrated in Fig. 3.8. Imagine you're scrolling through your Facebook newsfeed. When you log in, you typically see about 10 stories loaded initially. As you scroll down and reach the end of that list, Facebook automatically loads another 10 stories for you. This process of continuously loading more stories as you reach the bottom demonstrates how a while loop works in programming. Essentially, the loop keeps executing as long as a certain condition is true, in this case, until there are no more stories to load or until you stop scrolling. This example really helps connect the concept of the while loop to real-world applications. It shows how we can use this structure to create a seamless, dynamic user experience, like infinite scrolling, by repeatedly executing a block of code until a condition changes. So, in the context of programming, the while loop is powerful because it allows us to keep performing actions repeatedly, just like Facebook loads more stories when needed, making the experience smooth and efficient. Now let's talk about the for repetition structure and how the for loop works. The key function here is range, which is used to create a list of values that the loop will iterate over. When we use range with a single integer, like range 5, it generates a sequence starting from 0 up to, but not including 5. So it gives us 0, 1, 2, 3, and 4. If we specify two integers, like range 2, 8, it starts from the first number 2 and goes up to, but again not including the second number 8. So that would be 2, 3, 4, 5, 6, and 7. And for more control, we can include a third parameter like range 1, 10, 2. Here it starts at 1, goes up to 10, but increases in steps of 2, so 1, 3, 5, 7, and 9. Now regarding how many times this loop runs, it's determined by the range. When you write a loop like for counter in range, how many, the variable counter will take on values starting from 0 up to how many minus 1. So if how many is 5, counter will go through 0, 1, 2, 3, and 4. This concept is fundamental because it allows us to control iterations precisely, which ties directly into our overall theme of understanding control flow in programming. The for loop, especially with range, gives us a powerful way to execute code repeatedly, based on predictable sequences of numbers. Let's take a look at an example of a for loop. Here, we have the line for counter in range 10, followed by print counter. What this does is it sets up a loop that will run 10 times, with the variable counter taking on values from 0 to 9. The range 10 part is key because it generates a sequence of numbers starting from 0 up to, but not including, 10. Each time through the loop, the print counter statement outputs the current value of counter. So, when we run this code, the output will be the numbers 0 through 9 printed on separate lines. This example highlights how for loops are used to repeat actions multiple times efficiently. Instead of writing the same print statement 10 times, we use the loop to handle it automatically. In the context of our overall discussion, understanding this basic structure is crucial because it underpins how we automate repetitive tasks in programming, making code more concise and easier to manage. Let's take a look at some other examples of loops that you might encounter. These examples help us understand how versatile loops can be across different scenarios. For instance, there are loops in data processing, like iterating through datasets, or in UI programming, where they help manage repetitive tasks. It's important to see that loops are not just a single tool, but a fundamental concept that applies in many contexts. Recognizing these different examples reinforces the idea that mastering loops is essential for efficient programming and problem-solving. So, as we continue, keep in mind how these patterns show up in various applications and why they are so powerful. Now, let's look at some practical examples of using loops in our code. First, we have a simple while loop that counts from 0 up to 4. It starts with a variable called count set to 0, and then it keeps printing the value of count and incrementing it by 1 on each iteration. The loop continues until count reaches 5, at which point the break statement stops it. This demonstrates how you can control a loop with a condition and a break statement to exit when needed. Next, we see an example of filtering with a for loop. Here, we're iterating over a range of numbers from 0 to 9. Inside the loop, we check if the current number is even by using the modulo operator. If divided by 2 leaves no remainder, we skip the rest of the loop using continue. This means only odd numbers will be printed, which are 1, 3, 5, 7, and 9. These examples highlight 2 key concepts. First, how loops can be used to repeat actions efficiently, and second, how control statements like break and continue allow us to manage the flow within those loops. By mastering these, you'll be able to write more flexible and efficient code, which ties back to our overall goal of understanding how to control program flow effectively. Let's look at an example for the pass. When we talk about passing in this context, it's really about understanding how information or responsibility flows between team members or systems. This example will help illustrate the key points we've discussed so far. Notice how the pass is executed smoothly, ensuring that the right information reaches the right person at the right time. It highlights the importance of clarity and timing in communication. By mastering this concept, we can improve overall efficiency and collaboration within our projects. Remember, a good pass isn't just about transferring data, it's about ensuring understanding and continuity. This example ties back to our overall theme of effective teamwork and seamless processes. Let's take a closer look at expression values in Python. As you can see, the output shows that Python 2.2b2 was released in 2001, and the environment is running on Windows. Now, when we write simple if statements like if 0, the result is interesting. In Python, 0 is considered false, so the code inside the else block executes, printing 0 is false. Similarly, when we check if 1 or -1, both are non-zero, and Python treats them as true. So the statement if 1 or if -1 will evaluate as true, and the corresponding print statement confirms that. Finally, comparing 2 less than 3 returns true, which is printed as 1. The key concept here is that in Python, expressions evaluate to integer values, specifically 0 for false and any non-zero value for true. Unlike languages like Java, which have explicit Boolean types, Python uses this simple numeric approach for truthiness. This makes understanding conditionals straightforward once you grasp that is false and anything else is true, which ties into the overall theme of Python's simplicity and flexibility in handling logical expressions. Let's take a closer look at logical operators. First, we have the AND operator, which is binary, meaning it works with 2 expressions. It evaluates to true only if both of those expressions are true. So if either one is false, the whole expression becomes false. Next is the OR operator, also binary, which evaluates to true if at least one of the expressions is true. It only returns false if both are false. Then there's the NOT operator, which is unary, meaning it works with just one expression. It simply reverses the result. If the expression is false, NOT makes it true and vice versa. It's also helpful to compare these to Java operators. and in for and, for or, and for not. Understanding these can really help you write clearer conditional statements in your code. Overall, these logical operators are essential for controlling the flow of your programs based on different conditions. All right, let's look at how we can use logical operators in our code. Here, we have an example with an if statement that checks if a person's gender is female and their age is at least 65. If both conditions are true, we increment the senior female's counter. This demonstrates the use of the and operator to combine multiple conditions that all need to be true. Next, we see another example where we check if an IQ score is either greater than 250 or less than 20. The or operator here means that if either of these conditions is true, we increment the strange values counter. It's useful for situations where only one condition needs to be met. Then there's an example with the not operator. If a certain value isn't found, we print a message indicating that. The not operator essentially reverses the truth value of a condition, which is handy when you want to handle cases where something is absent or false. Finally, I want to highlight the use of the equals operator. It's a way to check if two values are different, such as in the example with I and J, where we print different values if they are not equal. Throughout these examples, the key takeaway is that logical operators like and, or, not, and equals allow us to build complex and flexible condition checks. These are fundamental in making our programs smarter and more responsive to different scenarios, tying back to the overall theme of writing effective decision-making code. Let's talk about augmented assignment symbols. These are shorthand ways to update the value of a variable. For example, instead of writing x equals x plus 5, you can simply write plus equals 5. It's a more concise and often clearer way to express that operation. However, it's important to note that you can't use the increment operator like plus plus in languages such as Java. Python doesn't support that syntax, so you need to stick with these augmented assignment forms. Now, this idea isn't limited to addition. The same rule applies to other mathematical operations too. Whether you're multiplying, dividing, or using modulus, you can use these augmented assignment symbols. So, for multiplication, you'd write equals 3 instead of x equals asterisk 3. For exponentiation, x asterisk equals 2. For division, x slash equals 4. And for modulus, x% equals 5. These symbols make your code cleaner and easier to read, especially when performing multiple updates to a variable. And understanding these is key to writing efficient Python code as we continue exploring programming concepts today. Let's talk about some key points regarding keywords. First, it's important to understand that in programming and data management, keywords are reserved words with special meanings. Because of their special status, we can't use them as identifiers, such as variable names or function names. Doing so would lead to errors or unexpected behavior in our code. This restriction highlights the importance of choosing meaningful, non-reserved names for our identifiers to keep our code clear and functional. Remember, the overall theme here is ensuring that our code is both correct and readable, and understanding how keywords work is a fundamental part of that. So, always be mindful of these reserved words when nomming your elements in any programming language. All right, let's talk about the keyword pass in Python. The pass statement is essentially a placeholder that tells Python to do nothing when it encounters it. You might wonder, why would we need something that does nothing? Well, it's actually quite useful during development or when designing your code. For example, imagine you have an if statement where you haven't yet decided what should happen in certain cases. Instead of leaving it empty, you can put pass there to make the code syntactically correct and continue building your logic later. In the example shown, you see multiple if conditions, and in some cases, pass is used to indicate that no action is taken for that condition yet. This technique helps you keep your code structure intact without causing errors, and you can come back later to fill in the actual logic. It's a simple but powerful way to manage your code during development, especially when you're still figuring out the details. Remember, pass doesn't do anything at runtime, but it plays a crucial role in keeping your code organized and error-free during the writing process. All right, let's wrap this up with a quick summary. First, we start with the total and the counter, setting the total to 0 and the counter to 1. The idea here is to initialize our variables before entering the loop. Then, we have a loop that keeps running as long as the counter hasn't gone past 10. This loop is essential because it processes each student's data or each step we need to perform, one at a time. Inside the loop, we add 1 to the counter each time, which eventually makes the loop stop once we've reached 10. This is a simple yet effective way to ensure our loop doesn't run forever. Finally, after the loop ends, we divide the total by 10 to get the class average. This step is crucial because it summarizes the data into a meaningful metric. Overall, these steps illustrate how we can use basic programming constructs, initialization, looping, and calculations to analyze data efficiently and connect to the broader theme of automation and data processing. Let's walk through this example of a class average program that uses counter-controlled repetition. The main idea here is that we're calculating the average grade for a class by processing exactly 10 grades. First, during the initialization phase, we set total to 0, which will hold the sum of all the grades, and we set grade counter to 1. This count helps us control how many times the loop runs, in this case, 10 times. Next, during the processing phase, we enter a while loop that continues as long as grade counter is less than or equal to 10. Inside the loop, we prompt the user to enter a grade, convert that input from a string to an integer, and then add it to our total. After each grade, we increment grade counter by 1, so the loop knows when we've processed all 10 grades. Once we've collected all 10 grades, we reach the termination phase. Here, we calculate the average by dividing the total sum of grades by 10, which is the number of grades entered. Notice that we're using integer division here, which truncates any decimal part, but in this case, it still gives us a pretty close estimate. Finally, we display the class average with a simple print statement. This example highlights the power of counter-controlled loops for processing a fixed number of inputs, making our program predictable and easy to understand. It also demonstrates how to accumulate data and perform calculations after data collection is complete, which is fundamental in many programming tasks. All right, let's take a look at this example of summing numbers with a for loop. Here, we're looping from 2 all the way up to 101, but notice the step size is 2. That means we're only going through even numbers, 2, 4, 6, and so on, up to 100. The goal is to add all these even numbers together. Inside the loop, we start with a variable called sum set to 0. Then, for each number in our range, we add that number to our sum. After the loop finishes, the total sum of all even numbers from 2 to 100 is displayed, which in this case is 2550. This example is a perfect illustration of how to use a for loop with a specific step, sized to process a sequence of numbers efficiently. It also shows how summing can be straightforward when you accumulate values in a variable during each iteration. Connecting this to our overall theme, it highlights how loops are powerful tools for automating repetitive tasks, like summing a series of numbers, which is a common operation in programming. Let's walk through how we calculate compound interest in this example. We start by setting the initial principal to $1,000 and the interest rate to 5%, or 0.05. Now, notice that the expression 1 plus the rate remains constant throughout the calculations, so it should be computed outside of the loop for efficiency. We then run a loop from year 1 up to year 10, which means we're calculating the amount on deposit for each year. The key formula here is principal times 1 plus rate, raised to the power of the current year. This exponentiation models how interest compounds year after year. As we go through each iteration, we display the year number alongside the accumulated amount, formatted nicely for clarity. The output shows the year and the corresponding amount on deposit, starting at $1,050 after the first year and growing to about $1,628.89 after 10 years. This process demonstrates the power of compound interest, how money grows faster over time because interest earns interest. Keeping the calculation of 1 plus rate outside the loop is a small optimization, but it highlights an important concept. Simplifying expressions when possible makes your code more efficient and easier to understand. Overall, this example ties back to our broader theme of understanding how compound interest works and how to implement it effectively in programming. In this slide, we're looking at how the break statement works within a loop. The loop is set to run from 1 to 10, but as soon as the variable x reaches 5, the break statement is triggered, and the loop stops immediately. So only the numbers 1 through 4 are displayed. This demonstrates that when break is used, the loop terminates early, and it doesn't continue to run until it reaches its normal endpoint at 10. You'll notice that the counter doesn't reach 10 as it normally would, because the break interrupts the process. This is a powerful tool when you want to stop a loop based on a specific condition, making your programs more efficient and controlled. It's an essential concept to understand as we explore how to manage flow control within loops effectively. Let's take a look at how the continue statement works within a loop. In this example, the loop runs through numbers 1 to 10. The key point here is that when the value of x equals 5, the continue statement kicks in. This means the loop skips the rest of the code inside the loop body for that iteration and immediately proceeds to the next number. So, what does that mean in practice? Well, the number 5 is never printed out, but all the other numbers from 1 to 10, except 5, are displayed. This demonstrates how continue can be used to selectively skip certain values during iteration without stopping the entire loop. It's a powerful way to control the flow, especially when you want to ignore specific cases without breaking out of the loop completely. And in this example, the output confirms that 1, 2, 3, 4, 6, 7, 8, 9, and 10 are printed, while 5 is skipped. The final line explains that we used continue specifically to skip printing the value 5. This concept ties into the overall theme of controlling loop behavior efficiently and making our code more precise in handling different cases.